Good morning, good afternoon, and good evening, everyone. So today we're going to be talking about the tangential and normal components of acceleration, right? So when we study the motion of a particle, it is often useful to resolve the acceleration into two components. So one in the direction of the tangent and the other in the direction of the normal, right? So if we write, let's say v is equal to the absolute value of that vector for the speed of the particle, right? So this is speed of particle. Then we have t, which is, so this is our unit tangent vector, right? From a previous, if we recall it from a previous video. Then we can translate that back to our velocity vector. And then the magnitude, which is just equal to this vector over its speed. So velocity over speed. And from here, we can say our velocity is just v times this function t, or times the unit tangent vector, right? And if we differentiate both sides of this equation with respect to t, well, then we get something here. We get a for acceleration is equal to, so we differentiate this v, and so we have v prime t plus v t prime. Okay, let's make it a function maybe. Then we put t prime here. Right, so here we use the product rule. And if we use the expression for the curvature, then we have another thing to consider here. So our curvature was the derivative of our unit tangent vector, right? And we say that's over the magnitude of r prime of t, so our tangent vector. And this was equal to, well, we can say it's equal to this over v, right? R prime of t, the magnitude of that is equal to v, our speed. And so we say that my magnitude of my unit tangent vector is just my curvature times my speed, right? And so we also had a unit normal vector that was defined. So we had a unit normal vector that was defined as capital N, which was equal to t prime, or our unit tangent vector, divided by its magnitude. Oops. There. Oh, it's in reverse, my bad. Goodness me. So it was the derivative of my unit tangent vector over the magnitude of that to get my normal. And so from there, this becomes, uh, so my derivative of my unit tangent vector is just equal to the magnitude of it times n. And again, we said that this is equal to my curvature times speed. And so from there, we have another thing to consider. So another formula here is the acceleration was our derivative of velocity times my unit tangent vector plus my curvature, my velocity squared, n, right? Okay. I hope that makes sense. Yeah. Okay. Okay, cool. And so now to find the tangential and normal components of acceleration. So we have a way of writing it, which was a sub t. I'm assuming that's how you call it. And a sub n for the normal. Oh my goodness. For the tangential and normal components. Of acceleration. Well, we now have something like this. We say that our A is equal to A sub t, or our tangential, times t, which is our unit tangent vector, plus our normal component times our unit normal vector, where here we define some terms here. We're saying that our tangential component is the derivative of our speed, and our normal component is our curvature and our speed squared, right? Okay. And then we can actually see this in an illustration, which I'm gonna quickly take a screenshot of. So we have two vectors. We have two things to consider for an acceleration. So these two vectors here, well, A is the acceleration, right? And then the other two vectors that consist of them when you add, these are the tangential and normal components, right? How do I know? Well, this is the one that's tangent. That's the one that's tangent. And this is the one that's normal. So this is perpendicular because it's normal. Then you sum those up, you get A, the actual acceleration for this thing. So here we're just trying to, how do I say this? We're trying to convey what acceleration is in a different way. We're trying to describe it in two ways here by adding these two, right? Okay. So let's actually look at what that formula is. Let's look at what in the world this is. Let's look at this formula 7. So the first thing to notice is that the binormal vector b is absent. So no matter how an object moves through space, its acceleration always lies in the plane of t and n. So it's an osculating plane. And recall that t, or the unit tangent vector, gives the direction of motion, and our unit normal vector n points in the direction the curve is turning. So next we notice that the tangential component of acceleration is v prime. So that's the rate of change of speed. And the normal component of acceleration is its curvature times v squared. So the curvature times the square of the speed. To contextualize this, we can think of a passenger in a car. A sharp turn in a road means a large value of the curvature k. I'm assuming that's a k, right? So the component of acceleration perpendicular to the motion, so we're talking about the unit normal vector, is large. That component perpendicular to the motion is large, and the passenger is is thrown against the car door. Okay. Anyways, let's not do that. So safe driving. High speed around the turn has the same effect. In fact, if you double your speed, our normal component of acceleration is increased by a factor of 4. Okay, this is probably some physics thing. Although we have expressions for the tangential and normal components of acceleration in equation 8, so it's talking about this thing. We have that expression. It's desirable to have expressions that depend only on, of course, our position vector. So r. At the end of the day, we want to make it all in terms of r. So that's easier to work with, right? And so to this end, we take the dot product of our v vector. So we're going to take the dot product of this thing. Let's quickly do that with a. Okay, as given by equation 7. So we're going to take dot product. So you want to find, or actually here constructing a formula that will help, that a more convenient formula. So that we only have to plug in position vectors in this case. So we're going to take the dot product of this velocity vector is equal to our speed times our unit tangent vector with a, right? So we're going to say v times a, or the dot product of those two things, is our speed. So when I'm not putting the arrow, I mean speed. The dot product of, so in this case, it's not a. We're going to do something in terms of a. So we're doing that instead. And then here we're actually going to get, if we manage to simplify this, v prime t dot product of t. We add our curvature, v cube t dot product again with n. Yeah. So here we basically, what we basically did here is we multiplied this to this. It's actually kind of like a DPMA. We multiplied this to this and this to that, right? Okay, and what else did we do? Well, this is now just equal to VV prime. Why is that? Because the dot product of our unit tangent vector by itself is just 1, right? And if we do the dot product of my unit tangent to my unit normal, well, I just get 0 because they're perpendicular. So this turns to 0. If I multiply this by 0, that turns everything to 0 here. And then here I just turn it into a 1, and so I'm left with that. And so therefore, now you have a nice looking formula here. So for number 9, our tangential component is just v prime, which is equal to the dot product of my velocity and my acceleration over my speed, which is actually now in terms of r. So it's r prime, dot product of r double prime, because that's acceleration. We divide it by the magnitude r prime to get my speed. So now this is everything in terms of r. And then lastly, using the formula for the curvature, now we have another important formula here for our normal component. So it's this curvature a squared, and here this is just my absolute value r prime t. So this is just the curvature formula for a, a plane. Oh no, in space, I mean, my bad, in space. That's k, this whole thing's k, or curvature. And I multiply it to my v squared. And my v squared is just my absolute value of my r prime t squared. And we can simplify this. Let me just adjust. So we can simplify this to be, well, the cross product of my first and second derivative over the magnitude of my first derivative, right? Because I just cancel this out. This becomes 1, this becomes 0. So that's the idea. And now I can make use of this formula of these formulas to find the normal and tangential component of any position vector I want. So I don't have to worry about the others. So let's quickly do that, yeah? Let's do an example here. So here we're being asked, or obviously, we're gonna go again through a particle. And this particle moves along r of t. So that's my position function with these components, d squared, d squared, d cubed. And we're being asked to obviously find the tangential and the normal components. Right? Particularly acceleration. Okay. So let's do that. So here we basically just find everything that we need to find. We need to find our derivative. We need to find our second derivative. And we need to find the cross product and the dot product and their magnitudes. So yeah, let's just quickly do it. So my r prime, or my derivative, is 2t, 2t, 3t squared. My double derivative is 2, 2, 6t. And now I'm being asked to find, okay, let's find the magnitude of my r prime of t. And so this is 2t squared, 2t squared, 3t squared squared, which is, let me try to mentally compute. This is, no, I'm kidding. 4t squared, 4t squared, 94th. So here we have 8t squared plus 9t to the 4th. So that's my magnitude of r prime. What else do we need? We need the dot product of those two. So let's also find that. Yeah, here I'm just filling in everything we need. So this is 2t times 2. That's, okay, let me just, and then we do another 2t times 2 again. And then we do 3t squared 60. And then this will give us 4t plus 4t, so that's 8t. Oh, and then we add, this is 18t cubed. Then can we simplify? I mean, I don't need to. And lastly, we get the, what else do we need? So we have the dot product, we have the magnitude of my first derivative. Oh, now I need the cross product and its magnitude. So let's get the cross product. Okay. Where am I? 2t, 2t, 3t squared. 2t, 2t, 3t squared. And my r prime is 2, 2, 6t. Okay. Then now I can do my cross product here. 2t times 6t, so that's 12t squared minus 6t squared. So that's my I. Okay, I can't. I'm gonna have to put it here. And then I'm going to subtract with my j. 2t times 60, so that's 12t squared again, minus 3t squared times 2, so that's 60 squared again. That's my j. Then I add it. Here I get 2t times 2, so that's 4t, minus 4t. Oh, I get my 0 for k. And so I have a vector that's 6t squared, 6, or minus 6t squared, 0. So that's my cross product. Now I get its magnitude. So I get 60. Oh, so I get 60 squared squared, 60 squared squared, 0 squared. And this will give me 36 t to the 4th plus 36 t to the 4th. And so I get 72 t to the 4th. Right? That should be it. What else did I miss? Okay, let me. Okay. What does this give me then? Will I take out my t squared? I have 72. I guess I do a 8 times 9 t squared. That gives me t squared 3. Now I have my 8. And then now my 8 here is 4 times 2. Then I have 6. Then yeah, that should be it. That should be it. Yeah, I was just trying to simplify everything. Yeah, so I get 6 to t squared. Okay, and then from there, now I have everything. I have everything I need. So my tangential component is the dot product over the magnitude. So the dot product is 80 plus 18t cubed. And well, it's here. My magnitude is square root of 8t squared plus 90 to the 4 to the fourth power. That's one of them. And lastly, my normal component is just the cross product over the magnitude. So my cross product is 6 square root of 2t squared over, again, this thing, 90 to the fourth. So yeah, it's really all about plugging in formulas. Um, that's pretty much it for tangential and normal components of acceleration that we have to consider. And yeah, I hope you guys enjoyed, and I'll see you all in the next one.